So now we're going to do a probability problem, and it's not too difficult, but the reason why I want to do it is because we're actually going to solve this problem in two different ways to illustrate a really interesting counting concept. And so let's start this problem by first looking at a couple of ways that we can satisfy the given condition. So it says 5 standard 6-sided die are rolled, and what is the probability that at least 3 of the die show a 6? Well, let's look at some cases that could work and one that couldn't. So if we get a 6, 6, 6, 5, and a 4, if we roll this sequence, this is good. This counts. But if we got a 6, a 2, a 3, a 1, and a 6, we only have 2 6s, so this wouldn't count. So now we just have to count the number of ways in which we can get at least 3 6s. So just so we understand this a little bit better, if we got 6, 6, 6, 6, and 6, this would work. All 5 6s is good. So the first way we're going to do this problem is just straightforward casework. So if we have to have at least 3 of the 5 die having a 6, that means the 3 cases that can work are if we have exactly 3 6s, exactly 4 6s, and exactly 5 6s. So we can just count these 3 cases, add them up, and that's the total number of ways that at least 3 of the die show a 6. And our denominator is going to be just the total number of ways in which you can roll 5 die. And so we can get 1 through 6 on each of the 5 die, so we're just going to have 6 times 6 times 6 times 6 times 6, which is 6 to the 5th power. So let's go on to our casework. So our first case, we have exactly 3 6s. So we need to choose 3 out of the 5 slots to have a 6 in it. So that's just 5 choose 3. And then the other 2 slots, we want to have exactly 3 6s. So that means the other 2 slots can't be a 6. So they can be anything from 1 through 5. So that's where we're going to have 5 times 5. And then for the case with exactly 4 6s, we need to choose 4 of the 5 slots. So that's 5 choose 4. And then we're going to multiply that by the number of ways, the number of numbers that the last slot can be, and that can be anything from 1 through 5 because we can't have a 6. Because remember, this case, we're having exactly 4 6s. So then there's 5 numbers that can go here. And the last case is pretty straightforward. There's only one way and you can have 5 6s, and that's this case right here. So that's the only case that works right here. So if we compute these values, we get 250 here. We get 25 here, we get 1 here, and if you add them up, you get 276. And so 276 over 6 to the 5th power is our final answer. And so we could simplify this further, but we really only want to show how the method works, so it doesn't matter too much. So let's move on to our second method, which is going to be a little bit more complicated, and it's called properties of inclusion and exclusion, or PIEs for short. And so the basic idea behind PIEs is we're going to use something called correcting for overcounting. So when we compute the number of ways in which at least 3 of the die show a 6, we're going to actually be doing a little bit of subtraction and correcting for overcounting rather than doing 3 separate cases like we did on the left hand side. So let's look at our first, the ways in which we can get at least 3 or more 6s on our 5 rolls. So we have to choose 3 slots to have our 6s, and then the other 2 slots, because we're not going to be doing casework like we did on the left, we actually can have 6 possible values for the next 2 slots, and we're actually going to be correcting for the overcounting that occurs here. So let's look at why the overcounting occurs. So let's look at this example that I gave on the that I'm going to give right here. Let's say we got 4 6s and then a 3, for example. And in this case right here, we overcount this a couple extra times. And the reason is because we could be counting these 3 6s for our initial when we're choosing our 5 choose 3, or we could be counting these 3 6s, or we could be counting these 3 6s, or we could be counting these 3 6s. So really there are 4 choose 3 equals 4 ways to choose 3 of these 4 6s. And so we're actually we really only want 1 because when we're doing our counting, we only want to count everything 1 time. So right here, we're actually counting it 4 times. So what do we have to do? We have to subtract 3 of them. So we're actually going to be subtracting 3 times the number of ways in which we can have 4 6s. So that's going to be 3 times 5 choose 4 times 6. Because remember, our last number, we put a 3 right here, but could actually be 6 possible values could be going there. Anything from 1 through 6. That's why we have the 6. And now we actually have to add back a little bit more because we subtracted too much. So what are we going to add back? So let's look at our last example, which is when we have 5 6s. So in our first value right here, we're looking at the number of ways in which we have at least 3 6s. But we count this way too many times over here. Let's say, for example, we chose these 3 6s, or we chose these 3 6s. We're actually overcounting. We're actually counting this case of 5 6s, 5 choose 3 times. So we're actually counting one thing 10 times, and we don't want to do that. We only want to count it 1 time. Now, in our second value right here, we're subtracting some of these. We're subtracting the number of ways in which we can have 4 6s. So in this example where we have 5 6s right here, we're actually counting 4 6s, 5 choose 4 times. So that's equal to 5. Because we could choose any of these 4 6s, and we're actually counting that 5 times. But remember, we also multiplied by 3. And so that's why we're actually overcounting this 15 times. So in total, we added this case 10 times. We subtracted it 15 times. So really, we've counted this case -5 times. The case of 5 6s, we've counted it -5 times. So how many times do we want to count it? We want to count it exactly once, because we want to count every possible sequence exactly 1 time. So right now we have -5, we need to add back 6. So we're going to add back 6 over here. Now, if you solve this expression right here, it's going to give you 276. So this is good because it's the same value that we got on our left-hand side with the other method. So we're going to have 276 over a denominator, which is the same, which is 6 to the 5th power. And so we get the same answer. So the purpose of this problem was really to show how we can use 2 different methods to solve the same problem. And the properties of inclusion and exclusion, which is the method we used on the right-hand side, is really just correcting for overcounting. We did some subtraction to correct for the number of ways in which we overcounted certain cases. And then we had to add back some because we subtracted too much. And so the properties of inclusion exclusion method seemed a little bit more complicated for this specific problem, but in a lot of other counting and probability problems, the PIE method, the properties of inclusion exclusion, where you subtract and add for overcounting, actually is a lot easier than this straightforward casework. In fact, it can save you a lot of time in math competitions in the future. So that's it for this problem. Thanks for listening.